So everyone, thanks for joining. This is a webinar on utilizing the full capability of existing inverters to bring about grid forming capability. As you might have just heard, we are recording this webinar. We're not going to be recording the audio discussion and the Q&A session that we will have at the end. So we're only going to be recording the presentation part of this webinar. Please do mute your phone. All of you must have been muted on entry, but in case that didn't happen, please do mute when the webinar is going on. Feel free to use Slido to keep sending your questions. If you're near your phone, you can scan the QR code and you can enter this ID number and join the Slido. If you're on your computer, you can go to slido.com and then enter this number, and you can add your questions, comments, feedback as things are going along. And once we finish the webinar and once we stop the recording at that point in time, we'll go through the questions and see how it is. And if we don't get through all the questions, we'll definitely, as we are uploading the material of the webinar, we'll also add a Q&A responses document. The material and all of the work that we are presenting in the webinar today is part of EPRI's Program 173 and the Unify Consortium. So if you want to know more about either of these research programs, feel free to send me a note, and I'll be happy to give you more information about the EPRI research program and Unify. So with that, let's get started. What's the context of this webinar? So we've all been talking about the increase of inverter-based resources. We've all been talking about how there can be different challenges that come up with these resources, the different kind of operation paradigms that come up. And along that same line, it opens up this topic of how can we best utilize the existing inverters on the system to provide the capability that we want. Now, this improved capability, this improved support that we want from these inverters can be in the form of what can be known as grid forming or advanced grid support. Now, we'll be using these terms interchangeably during the webinar. We'll try to prefer to use more advanced grid support because for reasons that will become hopefully obvious as we go through the webinar, it's, I think, a better umbrella term to capture the capability that we want. And talk in more details about what we actually want these resources to do. So what we'll cover through this webinar is we'll go a little bit into a conceptual background first to help provide a little bit of a technical rationale. It'll help set the stage of why we are talking about advanced grid support from existing inverter-based resources, why we are talking about how existing inverter-based resources can potentially be modified or retrofitted in order to bring about this capability. We'll talk about some equipment-specific simulation examples. So we'll look at a few examples of how this has been brought about in equipment-specific context, of course, from a simulation perspective, but using actual OEM black box models. We'll provide a little bit of system-level application examples that show how this concept can be utilized on a system level. And then we'll close out with some key recommendations and takeaways. Now, one overarching theme that we want to present as we go through all of this is that many or most of the inverters that are there on the system today, you might have heard that, oh, most of the inverters are grid following, which is this opposite context or concept of grid forming. We look at it from different perspective from EPRI side. Or the way we look at it is, there are a few of the inverters that have been designed to be specifically only grid following, but the majority of them are actually only operated as grid following, which means that they have the capability to do much more, but they are operated at an underutilized capability. And the aim here is to look further as with respect to how we can utilize that capability going ahead. So let's talk about the conceptualization of this advanced grid support. So we'll be using the acronym AGS for advanced grid support, and IBR is, of course, inverter-based resources. we'll use maybe acronym GFM for grid forming and GFL for grid following as we go along the webinar. So let's conceptualize this. Let's go a little bit into the technical background, and hopefully through this we'll be able to set the stage of how an existing inverter can be used to bring about advanced grid support, and what kind of retrofits, what kind of changes need to be made in their controls, what kind of maybe just tuning changes need to be brought about in order to bring about this advanced grid support. So the way we are looking at advanced grid support from inverter-based resources is we'll say that an inverter is said to provide advanced grid support if it prioritizes voltage and frequency control in the subtransient and transient time scale. So this is a time domain property. We'll go a little bit into a frequency domain evaluation, and we'll talk a little bit more details about that. But let's just setting the stage here that if the inverter in a reactive power versus voltage magnitude frequency domain scan exhibits a near constant gain between and if in a active power to frequency scan up to a defined cutoff frequency, it has near constant gain that exhibits droop and has a phase plus or minus between 45 degrees or 90 degrees. That's the range that we can have. And above that frequency, it has a low gain. And I'll explain as we go through this webinar, I'll explain in more details about these frequency scans. It's a newer kind of approach that here at EPRI and few of our other collaborators in the Unify Consortium, we have been working on developing some of these methodologies to help identify when does an inverter actually provide advanced grid support, or what kind of performance specifications is needed in order to ensure that an inverter does provide advanced grid support. So the way in which we can now classify these three different categories is there is a network support functionality in time domain, which is defined by this voltage and frequency control prioritized in the subtransient and transient time scale. There is a network support functionality in frequency domain because this frequency domain scan provides the similar kind of insight as this time domain scan or time domain. Frequency domain criteria actually provides boundaries on stability and robustness. Support in a stable or robust manner. All of this actually is structured in a way such that the exact control architecture does not matter. So it doesn't matter what kind of control elements are embedded within the inverter. It doesn't matter what kind of control architecture the inverter is using. These kind of properties can be utilized to identify from a black box perspective, is an inverter actually providing advanced grid support or not? And what we'll do is we'll work through it in and out. And I hope my voice is coming in fairly well and not cutting in and out. I'll try to stay closer to the microphone here. But we'll walk through these each of these categories one by one as we are conceptualizing this topic of advanced grid support and how can existing provide that. Kayla, just to check, is my voice coming in okay? I see a couple of notes coming in saying it's cutting in and out. Hey, I do hope it becomes better as we go along this webinar. We'll see how it goes. So I hope it's better now, but we'll go ahead. Okay, so let's talk about this concept from time domain. Let's talk about it from a controlled current source perspective, because we essentially want to see that, you know, if a inverter-based resource, we tend to think of it as a current source, and if that inverter-based resource as operates as a current source, if we can make that resource actually provide some kind of advanced grid support, then that actually sets the stage for the various kind of functionality that we want from these inverter-based resources. So just a little bit of background as to why do we call this conventional inverter-based resource as a current source. In all of our literature, in all of the terminology you might be hearing across the industry, you might be hearing about that an existing inverter is a current source. So let's actually dig a little bit deeper into why is it called as a current source. And the reason why we call it as a current source is that it has a fast current control loop that tries to ensure that a given amount of current reference is injected into the grid, and that happens in a very fast manner, which means that we can assume that an inverter-based resource is this controlled current source. And the assumption is that the current that is injected into the network is going to closely follow the reference command that is being generated. Now, what is a key aspect here is that the performance of this inverter-based resource is, however, now closely defined by how this reference current is generated or how this reference current is controlled. And we can now have different ways in which this reference is actually controlled, which can bring about different kinds of properties. So just because an inverter-based resource is a current source, it doesn't necessarily imply that it's always going to behave only in a given manner. It's always going to behave as an ideal current source where its current doesn't change. This controlled current source representation, we can play around with it and bring about different kinds of properties. So we'll walk through that. We'll walk through some very common implementations, and we'll see how we go from there. So let's take a very simple implementation where the current reference is fixed based upon power control or power factor control. So you have a fixed amount of P reference and Q reference. You have a measured amount of P and Q, and you have a phase lock loop that generates an angle. And this current reference is based upon this fixed value of P and Q, which is being injected into the network. Now, in this kind of a scenario, if you connect it to a grid where there is lower short circuit strength and you try to change the voltage of the grid, or you try to change the frequency of the grid, or you try to change the angle of the grid, you will get responses like this. So if you try to change the voltage, you will not see any change in active power. You will see some amount of change in reactive power when measured at this particular point, because this reactive power injection remains fixed and there is losses that come about in this particular inductor. When you change the frequency, again, you won't see any change in active power. You won't see any change in reactive power. And when you change the phase angle, you will see fast changes in active power, but they will be quickly controlled back to the reference, and you won't see any change in reactive power. What this essentially means is that this inverter provides no advanced grid services at all. So if it is on fixed power control, which is the situation with most of our inverters today, that they are operated in this manner, then the inverter by itself doesn't provide any form of advanced grid support. If we take it one step further now, where many of our inverters on the transmission system, many of the inverter-based resource plants on the transmission system actually have a power plant controller added onto them. So what this power plant controller does is it sends active power and reactive power commands down to the inverter. Everything at the inverter stage remains the same, but the power plant controller does some form of voltage and frequency control in a slower time frame. And for those who are interested in going into more details, the bandwidths of the various control loops are written down here with which these simulations were generated. And what you essentially see for a voltage change is you'll see a slower change in reactive power. For a frequency change, you'll see a slower change in active power. And for a phase angle change, you will see a response in this manner. Now, what's happening here is that the inverter-based resource is reacting in a much slower time frame to this variety of response that is coming in. It does provide some grid services, but that is more in the transient time frame, not in the subtransient time frame. So you see here that there is a slight delay in response. There is a slower response that comes about, but it does provide some support. Now, in a system that has a variety of synchronous machines, this kind of support from an inverter-based resource may be okay. It may be sufficient for the entire network. But as you get more and more inverter-based resources, this time delay that exists, or this entire region where no real support is provided, can become critical. So that is where we go down to the next stage, that we say that instead of having just a power plant controller providing updates to P reference and Q reference, if we actually have that same loop brought about at the inverter control itself. So we have an inverter that is now doing power and voltage control, but it has an added component to bring about voltage and frequency support at the inverter itself. Everything on this end remains the same. The PLL remains the same. The active way in which the current references are generated, they also remain the same. And you start seeing a very different response. So now you start seeing that for a voltage step, you see a much faster response from the inverter-based resource. For a frequency step, you start seeing a much faster response from the inverter-based resource. For the phase angle change, you see a much larger amount of response that comes in. So which means that this inverter-based resource now provides response and services within the subtransient time frame itself, as indicated by these particular responses. Now, these are important to track because if we now compare this with what an actual voltage source would do. So remember here, we kept everything as a current source. We didn't change anything in this controlled current source representation. All that we did was we changed the way in which this current reference gets generated. So now, if we actually compare this with a voltage source, which also does some form of power and voltage control, and it doesn't have a PLL, and it has an angle generated by the control, and it has a voltage reference gets generated, we see that for a voltage step, the responses are very similar. We see that for a frequency step, again, the responses are very similar. There is still a slight difference here in the response in this particular order. For a phase angle change, yes, this particular resource provides much more response to a phase angle change, but largely within the subtransient time frame, they are providing similar responses. So what does all of this imply, especially when we see it from a conventional inverter-based resource, especially when we see it from the lens of can a conventional inverter-based resource provide a change in advanced grid services? Can a conventional inverter-based resource be actually retrofitted to provide more capability to the grid? What it implies is, first of all, a recommendation from EPRI is that all of you, when you are presented with a concept of all existing inverters are current sources, whenever you hear the statement being made, our sincere recommendation is make it a practice to immediately ask these two questions. What is the control objective used to determine the current reference of the current source? And what is the expected response of the current source to step changes in grid voltage and frequency? The reason why we make this recommendation as to ask these following questions is it helps actually determine whether an inverter-based resource was designed to be grid following, or was an inverter-based resource only operated as grid following, and does it really have the capability available to provide more amount of support and services? We've seen that a current source can provide the necessary system support if its change in current injection is done in a fast and appropriate manner, and it can appear as a voltage source behind an impedance under certain topologies. So you can have a controlled current source appear as a voltage source from the grid's perspective. And we are going to call that an implicit or an apparent voltage source, as opposed to an explicit voltage source. And the reason for that is now, from this very initial concept, we can see from a time domain perspective that both an explicit voltage source and this implicit or apparent voltage source can help improve system reliability. And we'll show that in application examples as we go later on in this webinar. Now, why this is important as a concept is now this decouples this notion of voltage source, grid forming, advanced grid support. It decouples that entire notion from the control architecture. What it means is that we can now have a variety of different inverter-based resources actually provide this kind of grid support functionality. And if the time domain trace is insufficient, in being able to justify this kind of response, the frequency domain traces that we will show you now actually lend more guarantees in being able to determine whether a resource is actually going to provide this kind of grid support or not. And that's where we come upon in the frequency domain. So now we want to evaluate network support functionality in frequency domain. So we looked at time domain traces before, we looked at voltage step change, we looked at a frequency step change, we looked at a phase change, and we saw responses that suit what we really want from the grid. For a frequency change, we want active power to come up very fast. For a voltage change, we want reactive power to come up very fast. For a phase angle change, we do want the resource to move a little bit in order to provide the amount of response to the grid. Let's dig a little bit deeper now in frequency domain, because frequency domain evaluation of this kind of a property allows for scanning a variety of different frequencies and getting an understanding into, does this concept really hold across multiple frequencies? So we're going to use two references here when we look at frequency domain evaluation. We're going to use a first reference that actually evaluates how an ideal voltage source should behave from a frequency domain perspective. Now, there is a paper that is linked here for those who are interested in the details. Y'all can go into this. But to address this in simplifying terms, what this frequency domain functionality is it evaluates the transfer function of reactive power to voltage. So what we're essentially doing is we're going to evaluate how this transfer function of reactive power to voltage is going to change or vary, and look at its magnitude and look at its phase. What we want is we want a near constant gain across a wide variations of frequency, and we want the phase to be closer to 180 degrees. What this means is an implication is this, that if you have a increase in grid voltage magnitude, we want a decrease in reactive power injection and vice versa. That is what's the implication of a 180-degree phase. And we want this behavior to occur even for fast voltage changes. So we want this behavior to occur within one cycle. That's the implication of this 40 hertz kind of a range. Now, all of these values of frequency are around the nominal frequency. So this is across let's assume there's a perturbation across the nominal frequency, then that's when this frequency domain trace comes into play. Depending upon how close an inverter's transfer function is to these references, we can determine the level of grid strengthening that this inverter-based resource is going to provide to the grid. So this transfer function or this frequency domain trace allows us to determine the level of grid strengthening and the network support that the resource will provide. So now the same controlled current sources that we saw in the previous slides, we'll walk through them one by one. So we'll go back to see fixed power control, where we had P reference and Q reference being generated to, or being used to generate current references. And if we look at the frequency domain transfer function and compare it against an ideal voltage source. So the ideal voltage source has a near constant gain, and it has a phase close to 180 degrees. And we're going to be looking pretty much around in this frequency range, although the low frequency range also is important. And what we see is a response that it doesn't provide any amount of change for a voltage change. So this is the plot of the magnitude K. So if you think of a transfer function as Q divided by V is equal to K, we are plotting how K varies with frequency. So if K has a value closer to 0, what this essentially means is that for any change in voltage, there's going to be minimal change in Q coming out from the inverter. And the angle is also close to 0. And as we go towards this 4 to 40 hertz frequency range that we have defined, although the magnitude is slightly increasing, the phase angle is actually going away from what we want, and this can lead to a destabilizing effect. So the resource is not providing the kind of support that we want. Any change that occurs in voltage doesn't manifest in a change in Q. Any change in grid voltage is actually filtered out by the control. So the control actually filters out any change in grid voltage. Even if a change in grid voltage occurs, this fixed control will assume that there's no change at all occurring from an oscillation perspective, and it will not provide any support. This kind of response we don't want in the system. We don't want inverters providing this kind of a blue curve, because as you have more and more inverters in the system, it's going to be detrimental. Now, if we add the power plant controller to it, which was the second one that we had, we immediately see that there is some amount of grid support provided on the phase angle, which means that some level as the voltage changes, the reactive power is going to change in a manner that is desired, but the magnitude of change that we will see as the frequency of oscillation increases, the magnitude of change reduces. So what this means is that as long as you have a slow varying voltage on the grid, the power plant controller will be able to observe that slow varying voltage and command the inverters to change their reactive power output. But once you start having a fast varying voltage come in, the power plant controller is unable to track that fast varying voltage. It filters it out. And for faster varying voltages, it's as good as the inverter is doing close to Q control. So we also want the inverter to provide support in this faster frequency range or the faster frequency variation, because those kind of oscillations is also something that we want the inverter to support. So while having a power plant controller is okay for the low frequency variations or the slow frequency changes, the faster for voltage changes that might occur are not supported by this kind of a setup. We go to the next stage where we bring that down into the inverter level itself. And here we see a slightly better response. It's still not close enough to the ideal voltage source, but we start seeing slightly improved properties where we start seeing more support for the grid in these faster frequency ranges. We want these kind of resources to provide this kind of support as we have more and more inverter-based resources. So what is implied here? That to obtain good and robust grid support from inverter-based resources, we want them to provide non-zero and non-constant reactive power support. We don't want them to provide constant reactive power support, and that should occur for both slow and fast changes in voltage magnitude. And the frequency domain trace allows us to capture that kind of benefit or capture that kind of grid support and identify if a resource is really going to provide this benefit or not. What it implies is that the closed loop voltage regulation of the plant should have minimal delays, because the more delays there are, the higher frequency variations of voltage are not going to be captured and are not going to be, the resource is not going to react to that. Two potential options is that we can operate each individual inverter or turbine in voltage control mode, preferably with some form of droop or line compensation so that they don't fight with each other. Or we have lightning quick communication between the power plant controller and the individual inverters so that this higher frequency variation in voltage is not filtered out. There are two options. The plant developer can choose how they want to bring this about. What the frequency domain trace shows us is that the extent to which the plant would filter out higher frequency oscillations in voltage. And what it also shows that a controlled current source can be controlled to showcase properties that tend towards an ideal voltage source. So what this means is that depending upon how we change I reference for a controlled current source, which is what a lot of our inverters on the system are today. So if we have the flexibility to change that I reference, the current reference that they are operating at, we can make them bring about ideal voltage source properties, or at least tend towards it, which means that it does bring about more grid strengthening services, more advanced grid support. Now, just having this is not sufficient because it has no guarantees on stability. It has no guarantees on robustness. It has no guarantees on whether this resource will actually be able to contribute in a meaningful manner when you have a wide variety of changes occurring on the system. And that is where the third criteria for providing advanced grid support can come into play. And this is stability and robustness properties that we're going to be identifying. Now, this property is helpful in identifying whether a resource actually remains passive. So this is a property of passivity that we are actually going to be working towards. And again, there is a document in progress which goes into all the technical details that few of us are collaborating on. It should be released out soon. But what this essentially implies is that we want an active device on the grid to be seen as a passive device. So we want the grid to see this active device as a passive device. And the way we can bring that about from a frequency domain perspective is at low frequencies, we want the active power versus frequency transfer function to exhibit a property of droop, and its angle should be restricted between plus or minus 90 degrees. Now, the reason why it's plus or minus 90 degrees is that the greater this angle deviates from this kind of a threshold of plus or minus 90, there is more chance of a positive feedback occurring, and positive feedbacks can destabilize the network. So what this implies, and if let's say at a higher frequency, the angle does go above plus or minus 90, we want it to be low gain so that even if it does kind of bring about a positive feedback, it is a very small in magnitude and it's not going to impact the performance of the system. Now, these kind of caveats or these kind of cutouts have to be drawn out here to allow for different kinds of resources, to allow for wind, to allow for even rotating machines, to allow for batteries. They all have their own active power properties that need to be accounted for, and hence these kind of different ranges. What this means from a non-mathematical perspective is that if a resource increases its active power injection in a slow manner, it should result in a decrease in frequency and vice versa, which holds with our properties of droop, as we know. And at higher frequencies, the feedback loop that is there in an inverter should serve as a sink for oscillations. So what that means is if there is an oscillation occurring on the grid, the inverter should kind of absorb that oscillation and not respond back towards that oscillation. That's what this property is helping identify. Now, there are ways to define this from the way in which we would look at this from an inverter-based resource perspective. And what we'll do is we'll again go back to our ideal voltage source representation, use that as a baseline, and we will compare how different control structures that we had set up, how they actually map to this property of passivity. So the same color code as before. The blue curve is for the fixed power control. The orange curve is when the power plant controller was there. The green curve is when we had the frequency response and voltage response brought down to the inverter level. The red curve is the ideal voltage source. So what we immediately see is that the blue curve at low frequencies has an angle that is greater than 90 degrees, and it has a very high value of magnitude. So if we look at this transfer function in simplistic form as a gain M, then what we're essentially saying is that if the active power changes in a slow manner, the inverter-based resource is going to have a positive feedback because there's a negative sign here followed by a value that is greater than 90 degrees. It's going to have closer towards a positive feedback and can destabilize the frequency in the grid. And this is even more prominent at the higher frequency ranges. The inverter-based resource with a power plant controller, the property of droop comes about a little bit. The magnitude here is reflective of the droop at lower frequencies, and we start seeing a little bit more of a passivity property. The ideal voltage source has passivity for a larger range of frequencies. It remains more with this lower gain, and it only has a cutoff frequency that goes up after 10 hertz, which different resources will have different kinds of cutoffs. And the resource that we had with frequency and voltage response at the inverter level has increased passivity as compared to the power plant controller. Now, this is the kind of response that we want to aim towards. We want to aim towards a response that is towards between the green and the red. Because if we have our resources provide a transfer function response that lies between the green and the red, then we can have improved guarantees and on robustness of the system. So if you want to convert this into a what is implied kind of a scenario, then we want low gain when perturbations occur at high frequencies. So if you have higher frequency perturbations occurring on the grid, we want the inverter-based resource to actually have low gain in a transfer function, which indicates that it has more damping, indicates it has a better ability to serve as a sink for oscillations. We want the gain to be consistent with the droop when perturbations occur at low frequency. So that's consistent with promoting power sharing. Deadbands play a very critical role here, and we'll talk a little bit about deadbands in the next few slides. We need to be very cautious about deadbands when we are talking about now inverter-based resources and providing advanced grid support, because they can mask some of the capability that we are seeing here. Time delays between the plant controller and the inverter can also have an impact. So again, here we need to be careful about what is at the inverter level versus what is at the plant controller level. And again, a controlled current source can be controlled to remain passive and also act as a sink for oscillations. So we want to aim anywhere between an ideal voltage source and the controlled current source that is passive. So all of this was from a conceptual background. All of this was from simple models. You might ask a question, okay, all of this is good and fine from a theory perspective. Does it really apply to an actual inverter? Does it really apply to what a manufacturer might be able to provide? Does it really apply to inverter-based resource actually being able to do this in the field? So we looked at a couple of inverter black box models, and we're going to set two baselines here. What is termed as without advanced grid support, presently sold as grid following in the market by the inverter OEM. It has inverter level reactive power control with some amount of dynamic voltage support. It has a 5% voltage deadband. The gain outside the deadband is 5, and it has a continuously measured set point value. It has active power control at the inverter level without frequency support, and at the plant level, it has frequency and voltage support. And what the same inverter OEM, they also have a product on the market which is sold as grid forming, which has their advanced grid support. At the inverter level, they have some form of a droop-based control. And at the plant level also, they have frequency and voltage support. Now, if we take these two bookends, wherein you have without advanced grid support and with advanced grid support from this inverter OEM, and we also apply the loss of last synchronous machine test to this particular set of products, then without the advanced grid support, you do see voltage collapsing. You do see frequency collapsing when this last synchronous machine is tripped. And with the advanced grid support, you actually see a good stable response for both voltage and frequency. So the two baselines, as expected, the two baselines meet up well. Without advanced grid support, it fails the test. With the advanced grid support, it passes the loss of last synchronous machine test. So let's see now, what do we do? How do we configure? How do we create advanced grid support in the model that originally did not have advanced grid support? So what we did, and this is done with full coordination with the OEM. This is not to be done without coordination with the OEM. We worked continuously with the OEM to investigate these various properties, and that only after that we made changes to their black box models, and their settings are approved by the OEM to say that yes, this makes sense, because we also don't want to put settings into an OEM model that don't make sense. So what we did was we made the following changes. We reduced the deadband on the dynamic voltage support. We increased the gain. We made the set point for voltage control, rather than a continuous measured value, a fixed nominal value. We reduced some low pass filter time constants. And on the active power side, we added, so this has droop, right? So this has many inverters within the plant having a fixed voltage support, fixed voltage set point, but with some droop, so that they can move around as based upon their value that they see at that particular node. On the active power side, we again reduce the deadband down to a low value, and this can be a concern in some of your minds, so we'll address that as we go further. We added some droop on the active power frequency support with fast frequency response, and we reduced the amount of filtering that occurs on the PLL frequency. So what do we get now? We applied the same test, and now the configuration, after the configuration change, when we compare it with the original advanced grid support, we see a response that actually achieves a stable response. Now you might say that yes, there is still a transience here that is undesirable, and that is recognized, that we do recognize that this transient can be undesirable when you do this kind of a test. So we'll actually start looking at this more from larger system studies. But from a conceptual perspective, it is now possible to have a configuration change in an existing inverter-based resource and bring about advanced grid support from these existing inverter-based resources. Note that this is not a complete control architecture change. It is more about tuning some of the existing inverter-based resources and updating some of their existing configurations to bring about this response. So a few things of concern here, though. We put a very small deadband. We've set a very small deadband here of around 1 to 1.5 millihertz. And noting that the grid frequency is never constant, this could be an issue. That we've all known that our conventional thinking has been deadbands are needed because frequency is always moving in the system. And will that cause the resource to continuously responding? So we'll address that. Reduced low pass filtering that we had, can that cause an inverter to respond to every angle change that occurs in the network? And having a fixed nominal voltage reference and gain, there is a question of how would that value be identified? Is this more increased coordination required within the plant with multiple inverters? All of that needs to be addressed. So we look at this deadband aspect first and this additional low filtering. What we did to address that is in the same test, we now put some random load variation. So we have two types of random load variation that we're putting in here. We have one current source that is just injecting random amount of current within a certain magnitude tolerance. And we also have a constant impedance load that is continuously changing the amount of load it is drawing on here, again within a magnitude of tolerance. And here is the response that we see. So essentially now that both inverters are or both configurations, with the configuration change for advanced grid support and the configuration that had initially advanced grid support enabled in it by default, we see that both of them again respond in a very similar manner. Both of them are responding to this continuous change that occurs in load. The low or small value of deadband or the reduced filtering in the frequency is not resulting in an instability. So it's not resulting in any kind of resource that is changing its response continuously. It's actually well aligned with the kind of advanced grid support we might want. It does have an implication. It does have a consequence, especially for battery energy storage systems. And that is something that we have to recognize because there are many grid codes that still allow deadband with advanced grid support. But what this concept has shown us is there are different ways in which an allowed deadband is inferred. If you talk to a resource, inverter-based resource that does not provide advanced grid support, their inference of deadband is that, so let's assume here that the deadband is 10 millihertz or 15 millihertz in this example, and we make a frequency change of 10 millihertz within the deadband. So a resource that does not provide advanced grid support will actually not change its active power at all. This is for an inverter. This is for a 3 megawatt inverter. It's operating at 50% of its operating point or range before the change occurred. And this inverter is not going to respond at all for any change of frequency that occurs in the deadband. But actually, and this has a plant controller also added on to it. But actually what we want with advanced grid support is we want this transient change to occur, and it can then be slowly brought back down to respond to this or sit across this pre-disturbance value after some point. What this means is there are potentially two hierarchies of deadbands that might exist in an inverter-based resource that provides advanced grid support. And that is something that as you all are developing grid codes, and if you have a deadband in the grid code, you have to be careful in defining an additional transient response requirement in the grid code so that you get this particular change in response and you don't get this response. And with the configured advanced grid support, we again get the change in transient response, and it brings back down the value of the active power back within the deadband. So we have to recognize that this response here in blue is something that we don't want in the system. This response in green or orange is what we do want in the system. So there can be two layers. There can be a fast inner layer without a deadband or very minimal deadband that is allowing for this transient response. And we have a slower outer layer of control with a deadband that helps bring this frequency or active power back to the nominal value or pre-disturbance value. Now, what is the implication here from a battery energy storage perspective? Because if we apply a same random change in frequency that occurs every day in the grid, again, here we have a deadband of 15 millihertz, And we are going to continuously apply a change of frequency in the grid, which is well within the deadband. And we're going to apply this change once in every a couple of seconds. If you do not have any advanced grid support, the resource is going to sit at this particular blue curve. But if you have the configured advanced grid support, or if you have a resource that has advanced grid support by default, then you will see these kind of orange or green changes occurring. So again, what this means is that the inverter can do it, but an OEM should check with their battery OEM to identify if such an operation is acceptable. What this also means is that anybody who's looking at defining grid codes for grid forming and expects a battery resource to operate in this particular manner, if they have to get the same levels of guarantees of lifetime and cost, the battery OEM has to be consulted to understand if this kind of an operation is going to be acceptable, or if this continuous up and down cycling of the grid forming resource can degrade the battery life. And that is an aspect that we have to consider. And it could add a potential cost to the plant that has nothing to do with the inverter side. If we look at the same kind of a response with the nominal voltage set point set, if we have the response with the low value of deadband, and we just compare how these resources function for a low value of SCR, again, the configured advanced grid support performs in a manner which is very similar to the product from the OEM with advanced grid support that they have on the market. Remember, all of this is with OEM black box model. So what this is essentially meaning is that there is an inverter OEM's product that they have it operating without advanced grid support right now, but and that's because of the connection rules and whatever mechanisms were available to them. But they can be configured to provide advanced grid support functionality. And when they do that, they tend towards some of their advanced grid support functionalities that they provide in their other products. This has to be done in a careful manner. It has to be done with consultation with the OEM. It has to be done with consultation with the plant developer. It has to be done with consultation with the battery OEM. But it's now possible to potentially retrofit our wide fleet of inverter-based resources that are there today to provide more and more of these advanced grid support services. How does it compare in frequency domain for this OEM's black box model? We see that the OEM's product, which was without advanced grid support, in the reactive power to voltage frequency trace, we looked at the 4 to 40 hertz range. It has a value of angle that is closer to the controlled current source blue curve that we had seen before. It has doesn't have a constant value of gain. But all the other three modes, that is with advanced grid support and the configured advanced grid support, actually provide very similar response as we had seen earlier in our conceptual diagram. And how does it translate on the passivity side? Again, this is with the OEM's black box model. We see that without advanced grid support, they do have a low angle, but the magnitude is extremely high. And with the both with the advanced grid support and the configured advanced grid support, they do have closer to 0 degree. They do have droop established. They do have a response that lies in between. And as we had told last time, that we want a response that sometimes lies ideally in between the two curves, which is what their full advanced grid support functionality does. And their configured advanced grid support tends towards it. What this means is that we can, if we are even able to change many of our fleet to go from the blue curve to the green curve, this blue curve is already there in the field today. It's already deployed. If you are able to translate that to the green curve, we will dramatically increase our system reliability. We will dramatically increase our capability of utilizing the inverter-based resources. We compared this with one other OEM also. So this is now two OEMs being compared. And what we saw that two OEMs, so OEM 1 was the same OEM that we saw on the previous slide. OEM 2 is the new OEM. They're both functionalities without advanced grid support show similar kind of trajectories. And both of them can be configured to provide some amount of advanced grid support, both in the reactive power to voltage trace and in the active power to frequency trace. If you want to know more about how to generate these curves, feel free to contact us. We have work in our EPRI research programs that help you can generate these curves for black box models. We have tools available that can help you generate these curves. So if you want to know more about how to generate these curves and how to actually verify if an inverter-based resource is providing advanced grid support or not, feel free to contact me and I will be able to provide more insight into some of the tools that we have that can help generate some of this additional insight. So all of this is good from an individual inverter perspective or an individual plant perspective. Really, does it really work in an application study? Does it really have any benefit on a system? Let's take a look at that. So we'll talk about 3 different application studies. We'll go into only one. We'll go into details of only one study because that is quite interesting. But we'll cover on a broader level 3 different studies. So the first study is something that we did a few years back, actually, when we started investigating this concept for the first time. And this is a toy system. It has some amount of a load center, 2 load centers that are there. It has PV and wind and connected through long transmission lines. There's a paper that is there here, which anybody who's interested can go read in more detail. And this was kind of the first work that we had done, which showed us that that there is a possibility of configuring existing inverters to provide more of this support. And we saw that when we disconnected the synchronous resource, the 100% inverter system was able to maintain stability. Now, yes, some of these variations can be larger depending upon how much flow was there across this resource, but it can be managed depending upon sizing and siting of the resources. The second study that we did was actually, we did more about a stability analysis also, and this was a little bit on the distribution system, trying to identify that if we have many resources on the distribution system and they are all connected together, and you do open this grid tie, then if you have some of this advanced grid support coming into the distribution system, can the distribution system manage itself? Now, an interesting point here is that when we were doing this work and we spoke to the OEM and we brought about these results, one of the reactions from one of the OEMs was, yes, actually, we did look into this earlier for a distribution system concept, but at that time, we didn't look into it further because there were concerns about unintentional anti-islanding causing an issue and a system running as usual with unintentional anti-islanding. And that's a very legitimate concern. And it actually holds even for grid forming technology, that grid forming technology or advanced grid support technology in the distribution system with unintentional anti-islanding that might, or unintentional islanding that might occur, there is a safety concern that can happen, and this is something that we do have to take into consideration. But that conversation with the OEM actually did give us some more guarantees that this concept could actually work for existing inverters. There are other caveats associated with it, with protection and with safety and health, which is very important and needs to be considered. But that is a concern that occurs even for advanced grid support or grid forming. But an example study that we did was that, okay, that if we do open the switch, there is a way to get about stable responses. The third study that we did was actually on a weak grid test case network that was recently published by a system operator. And what that has is it has a very simplistic setup. It has an inverter-based resource connected at this bus. It has another inverter-based resource connected at this particular bus. There is a connection to the rest of the system here, and there is some load here. And what we're going to do is we're going to successive line outages are going to occur. And with these successive line outages, so first this one will go out, then this will go out, and then this will go out, leaving behind these 2 inverter-based resources only through a very weak tie to connect to the rest of the system. So we're going to test this setup up first with an OEM model for these 2 inverter-based resources. So these 2 inverter-based resources represented with an OEM 1 black box model, initially without any advanced grid support at all. And no prizes for guessing here. We do see an unstable response that without any advanced grid support, there is a lot of reactive power deficit in the network. The power flow doesn't converge for some of these scenarios. And as we keep adding faults and opening lines, the system goes unstable. So without any advanced grid support, a very intuitive response that things are going to go unstable here. So we said, okay, there is a reactive power deficit in the system, which means that some more resources are required to provide reactive power support because these resources have reached their limit. So we add two new inverter-based resources, IBR3 and IBR4. And now we're going to compare across two different OEMs also. So IBR1 and 2 are OEM1 model, and IBR3 and 4 are going to be the OEM2 model, all black box models. And now we're going to consider different combinations of advanced grid support and see how they line up. If we just keep IBR1 and 2 and have configured advanced grid support for them, we get one improvement in response wherein the first line outage is stable, but anything after that is unstable. If we have the first two inverters without advanced grid support and the new inverters providing advanced grid support or grid forming as per the OEM2, then we are able to get a stable response through all three line outages. So line outage 1, line outage 2, line outage 3, we are able to get a stable response. If we actually keep configured advanced grid support on the first two inverter-based resources, and we play around with either having regular advanced grid support or configured advanced grid support on the third and fourth inverters, we get stable responses in both scenarios. So what this means is now, firstly, having all four inverters with configured advanced grid support actually provides a much improved response. It provides a well-damped response. It provides improvement in damping as shown by the orange curves. So that's definitely something that we should aspire towards. Even if we have regular advanced grid support and configured advanced grid support as a mix and match, again, that provides a good response on the system. What this is all leading towards is that we as an industry probably need to move away from having no advanced grid support on these inverter-based resources at all. We either need to move towards having just vanilla advanced grid support on newer inverter-based resources coming in, or we need to configure our existing resources to provide more of this functionality and capability. So the delivery, to close out what we have in this webinar, is the delivery of this advanced grid support does not depend on a specific type of control architecture. We have tested it out with two different OEMs. They have a wide variation in control architecture within their black box, but the concept holds. The concept of what we were trying to conceptualize of where should the support come in, what kind of changes need to be made to configure it, that does hold across the two different OEMs. It doesn't matter whether a source is a controlled current source or a controlled voltage source. We should probably stop using those comparisons of whether a resource is a current source or a voltage source, because it all depends upon how you control the current that is injected by this resource. And we can get about a variety of grid support functionality. In addition to time domain, we should probably start using frequency domain characterization also much more, because they can help us determine whether an inverter-based resource, what level of capability does it have to provide this kind of advanced grid support. And an existing inverter can be configured to provide this kind of advanced grid support. And if it can improve the stability and reliability of the network and lower the burden on new resources. Now, some of you may ask, all of this is good. All of this is good theory. All of this is good from a conceptual perspective. So what? Like, where does this lead to? What is the next step in applying this towards the system? First question is, does it imply that we should not be looking at any new types of control? Does it imply that oh, because of this, we should not be considering any newer kind of inverter-based resources? Definitely, not at all. It doesn't imply that at all. What it does imply is that we need to be working towards improvement in control techniques that improve the robustness of the system. But at the same time, we should also look behind into the fleet that we have and see how we can improve their ability to support the grid going further. And the more we can do to improve that, the greater overall benefit it has to the system. So what is the application of this work now? Given that we just showed that OEMs already have advanced grid support functionality, they already have products in the marketplace. Why should we go back and look at the resources that we already have in our system? Why should we try to reconfigure something that is already there on the network? What is the application of this? From our perspective, there are a few applications that come up here. Firstly, there are scenarios or situations where it is not possible to put a newer inverter-based resource product into the grid at that particular location. Maybe because the interconnection queue doesn't allow for it. maybe because the location on the grid doesn't allow for it. Maybe the type of resource that is there is unable to provide any kind of newer functionality. So all of these three constraints can actually hamper the delivery of advanced grid support in that particular scenario or particular situation. So having a knowledge about reconfiguring, having a knowledge about repowering, having a knowledge about maybe changing some of the tuning rules within the resources that are there in the system at that particular location can improve the reliability in that local pocket if other scenarios prevent newer technology from coming in. Retrofitting of the existing inverters does improve their stability and robustness. There are certain regions now that are offering incentives for a certain time period, that in a limited time window, there is an incentive being offered for newer existing resources in the system to configure themselves to provide advanced grid support. So having knowledge about some of this background can actually help speed up the transition of getting increased reliability on the grid. It allows for increased utilization of the capability of our existing resources. We are able to maybe drive a Ferrari like a Ferrari rather than drive a Ferrari like a Hyundai Elantra car or something like that. We are able to actually utilize the capability of our resources to the full extent. Now, the third part here, or the fourth part here, is having this background of how an existing resource could be reconfigured to bring about advanced grid support actually helps define or determine market incentives, because it helps us identify what constraints might exist if we have to define market incentives for these resources to provide this kind of capability. And it helps bring about a more informed decision on system reliability. It helps bring about a more informed decision on the way in which we are utilizing our resources, the way in which we are utilizing the equipment that we have on our system, the kind of newer assets that we want to bring into the network. I think overall it helps bring about that decision making. We have put up a sample questionnaire, a suggested questionnaire that if you're a generator owner, if you're a transmission provider, you're a transmission operator, transmission owner, planning coordinator, you can provide two inverter OEMs to ask them that, hey, is your product capable of being configured to provide this advanced grid support without requiring an entire full software upgrade, without requiring an entire new commissioning procedure, without requiring an entire new product to be put in place? Is it possible to reconfigure? Is it possible to retrofit? We've put up a sample questionnaire to see that, to get to know which plants can actually provide more of the support, which plants can be retrofitted, which plants cannot. So with that, I'll close the webinar. Thank you so much for attending. We will stay online for question answers and discussion, but at this point, we will stop the recording. So Kayla, if you could stop the recording, please.